All right, team, let's get right into it. Welcome to today's explainer. For this one, I'm going to be adopting the role of your QA lead and senior performance engineer. We're going to be conducting a postmortem report on a very specific, highly complex system process. But instead of looking at server logs or code commits today, we're actually looking at chemistry. We're going to treat a chemical reaction exactly like a complex batch job execution. By applying the analytical frameworks of software engineering and performance metrics, we can unlock a totally fascinating new way to understand stoichiometry, system bottlenecks, and resource depletion. Okay, let's dive into this performance review. Now, to the untrained eye, sure, a burning match is just a burning match. But to a performance engineer, this is literal visual evidence of a live batch job execution happening right in nature. We have our inputs, the chemical composition of the match head and the oxygen in the air, and they are being violently and rapidly transformed into our outputs, which are heat, light, and new chemical compounds. This isn't magic. It's a strictly governed system process. And just like any IT system, it has strict rules, scaling parameters, and hard hardware limits. So here's our quick agenda for today's postmortem. 1. The conversion script. 2. System scaling and benchmarks. 3. Identifying the system bottleneck. And 4. Real-world performance metrics. Kicking things off with Section 1, the conversion script. Every great system framework has a pioneer, right? Well, meet Antoine Lavoisier, a French nobleman from the late 1700s. You can basically think of him as the ultimate systems architect, powdered wig and all. He established the foundational rule for literally all of our batch jobs, the law of conservation of mass. He stated that in all operations of art and nature, nothing is created. An equal quantity of matter exists both before and after the experiment. In software terms, matter is neither created nor destroyed, it's merely reallocated in memory. You absolutely cannot have data loss during a chemical execution. The crucial point here is that a chemical equation acts as our balanced conversion script. Let's think about the combustion of methane. That's the principal component of natural gas. For our reactants, or our system inputs, we have methane and oxygen. For our products or system outputs, we have carbon dioxide and water. But wait, if we examine this raw, unbalanced script, the atomic counts don't match up. We have 4 hydrogen atoms going in, but only 2 coming out. Lavoisier's architecture strictly forbids this kind of data loss. To fix this, we've got to balance the script. By adjusting the coefficients, those are the large numbers in front of the molecules, we ensure 0 data loss during the transfer. We just add a 2 in front of the oxygen input and a 2 in front of the water output. Bam! Now, 1 molecule of methane reacts with 2 molecules of oxygen to produce exactly 1 molecule of carbon dioxide and 2 molecules of water. Our inputs perfectly match our outputs. The script is validated and ready for deployment.
Moving right along to Section 2, System Scaling and Benchmarks. Obviously, you can't run a commercial manufacturing plant by counting individual invisible atoms. We need a system scaling parameter. And that massive constant is Avogadro's number, 6.022 times 10 to the 23rd power. This is the exact definition of a mole in chemistry. Just like a dozen means 12, a mole means 6.022 times 10 to the 23rd objects. This massive constant is the key that lets us batch process atomic level calculations into macroscopic, measurable quantities that we can actually weigh on a scale.
This is our logic bridge. To establish our performance benchmarks, we take our molar amount, which we derive straight from our balanced conversion script, and we multiply it by the molar mass of the substance. This simple method translates our theoretical script into real-world grams and kilograms, and this calculation gives us what we call the theoretical yield. Think of the theoretical yield as our optimistic benchmarking. It is the absolute maximum output our system can produce if every single line of the script executes flawlessly with 0 physical interference.
Next up, Section 3, Identifying the System Bottleneck. In chemistry, this bottleneck is called the limiting reactant. By definition, the limiting reactant is the specific reactant that is completely consumed first in a chemical reaction. It completely dictates the absolute maximum amount of product that can be formed. Listen, it doesn't matter how much of the other materials you have left over, the limiting reactant is the ultimate system bottleneck that restricts our calculated capacity.
I want to strictly apply a 0 conditional logic rule here so this really sticks with you. Ready? If one reactant is consumed entirely, the process stops. Period. The execution halts instantly. Any other input materials that haven't been used are simply left over as excess starting material. They are essentially stranded in memory, completely useless to the current execution cycle. Let's map this directly to a software engineering analogy to make it crystal clear. Imagine we're synthesizing water, H2O, from hydrogen and oxygen. Think of hydrogen as a massive database of username strings. Now think of oxygen as a strict allocation of unique IDs. And the water product? That's the fully instantiated user object. If our system runs out of unique IDs, our oxygen, we are entirely bottlenecked. You cannot instantiate even one more user object, even if you have millions of username strings just sitting idle in your database. The oxygen is the limiting reactant. It completely dictates the total allowable output. And finally, Section 4, Real-World Performance Metrics. When we contrast the data between our optimistic benchmarking and physical reality, a very clear pattern emerges. The actual yield is almost always lower than the theoretical yield. Why? Because of system side effects. In chemistry, we call these side reactions. Sometimes reactants react in unexpected ways, or material gets lost during physical transfer, or the environmental conditions aren't perfectly calibrated. The gap between that 100% theoretical benchmark and the actual yield is what we call our output variance. To see this at a commercial scale, think about massive real-world fermentation tanks. Here, bacteria are essentially acting as biological servers, executing the batch job of fermenting grain to produce ethanol and carbon dioxide. In massive deployments like this, managing variance is literally everything. Engineers found that the biological process became significantly more efficient after optimizing the temperature of these copper tanks. However, even with millions of dollars invested in heat optimization, the actual output remains slightly lower than the theoretical maximums. Physical reality always exacts a toll. So let's drill down and finalize our post-mortem takeaways for this chemical batch job. First, we must report that actual yield is almost always lower than theoretical yield. Second, our total yield was significantly impacted by resource depletion, specifically our limiting reactants running out. Third, as seen in commercial applications, the process ran much more efficiently after heat optimization was applied to the environment. And finally, the overall system variance is slightly higher than our perfectly optimized benchmarks initially predicted. Chemistry isn't just lab coats and beakers, guys. It is the ultimate study of resource management, constraints, and yield optimization. So, I'll leave you with this final challenge as we close out today's explainer. Take this analytical framework back to your own work. Think about your own bandwidth as your theoretical yield. What hidden side reactions or memory leaks are acting as the limiting reactants restricting your actual yield in your daily processes? Identify your system bottleneck, balance your script, and go optimize your output. Thanks for joining me, team. End of report.